Can you hear me now, Jennifer? Just making sure.
Yes, I can hear you.
Okay, good, awesome. All right, so good morning, everyone. For some of you, it may already be afternoon, and I see we've got folks from not only the United States, but Canada. Welcome. This should be hopefully a very eye-opening session for you. I'm kind of curious. We have a couple polls that Jennifer and I put together for this. And we'll push those out in just a second. But our session objectives today are to talk about what is the study of mathematics. And I think this is something that is overlooked in instruction with students and with parents and teachers as to how does math work. Then what does it mean to do math? What does that mean? How do we do math? Then why is that important? And then what does research show is needed to help students that are struggling, and some examples of some research-proven methods. Jennifer, get ready to push that first poll out if you let me.
Okay, so we're going to do you feel confident teaching math, correct?
That's right. One of the questions I'd like to get a poll, get kind of an idea from you, the audience, is what's your comfort level in teaching math or understanding math? And this is really an interesting thing for me to get feedback on, because if all of you say you're confident and comfortable teaching math, then that's going to be a very different conversation that I will have with you than the vast majority are where I was when I came out of school, and most of my time as an adult learning, trying to figure out how does this go together? Why do we have all these different things, and why are fractions and division and multiplication necessary? So I'd be very interested to see those of you that are here. How do you feel? What's your confidence level in doing mathematics?
We still have votes coming in. If everybody just clicks on the yes or the no, we can go ahead, and it looks like they're starting to slow down now, so I think we have about everybody voted almost. Oh, it's coming in again now. Hold on a second. Okay, good. So I think we are just about done with this one. Oh, yeah, they're still voting. This is great. I never usually get this much participation on a poll, so this is wonderful. Okay, so I'm going to go ahead and close it.
I appreciate people participating.
Absolutely. Let's see. And now I'm going to share the results. So, Dan, I don't think it shows on your screen, so I'm going to go ahead and just read off the results. So, poll results, 39% say yes, they are confident, and 61% say no.
Wow. That's a pretty interesting split there.
Yeah.
And I'm glad to have both groups well represented here. So we're going to do the next poll in just a second. So I'm kind of curious. When I talk to people, it's very interesting what they think mathematics is, or the study of math is. And so part of what I try to do as an individual is, when I was in school, I didn't get math. Math made no sense to me. When I graduated high school, I actually did not complete Algebra 2. I wanted to go to college and become an architect. Well, you can all imagine how that worked. No, I did not become an architect. And in the process of going through all of that, got married, had 3 wonderful children, and it wasn't until I was much older that I actually needed to explain to my own kids how math worked. And my wife and I, who is my co-author on the Perception series, asked the question, how do we help our kids? And our middle son and our daughter both have dyslexia and dyscalculia, and they were struggling tremendously with math. So it took some time for us to figure out, how do we teach them? How do we reach them in a way that's going to be beneficial for them to be able to use math in their lives? And so what I'd like to do now, Jennifer, if we can push out the other poll, is this is a multiple choice poll. You can actually select more than one item here, but I'd like to ask you, what do you think the study of math is? And there are some answers here that you can pick. I'd like to hear what you think, what the audience thinks the study of mathematics actually is.
Okay, good. We've launched it, and we've got votes coming in. So let's go ahead and see how this goes.
Remember, you can pick more than one thing. You can pick one thing. You can pick all of them if you want.
Still coming in. It's looking good, though.
Good. Well, it's just interesting because I ask this question at every workshop that I do in order to understand that for most of us, the way we look at mathematics is kind of been skewed a little bit. And I think that's partially due to the instructional methodologies that have been used and what is emphasized in mathematics. And when we can actually have some explanations of things, it changes the way we look at the math. And that's really what I'm about, is helping people change the way they look at mathematics.
Okay, so we have our results up, and
okay.
So what is math? What is the study of math? The first choice was numbers and values. 91% selected that.
Good.
The next one is facts. 64% selected facts.
Okay.
Algorithms, 69%.
Okay.
Shapes and space, 76%.
Okay.
And last, arithmetic, 60%.
Great. Well, for those of you that pick numbers and values, very good. Numbers and values, or numbers and quantity, is part of the study of mathematics. And mathematics is really the study of numbers, quantity, shapes, and space to begin with. And so the number 1 and the number 4 are two of the pieces here in this slide. Facts and algorithms are what oftentimes are emphasized in doing mathematics. As a student in school, it was like the facts were something that was just done over and over and over again. But I was never taught understanding as to why the facts were important. What was the purpose of the facts? What was the purpose of understanding the algorithm and being able to do it? And arithmetic is really an area of mathematics. It's the use of addition, subtraction, multiplication, and division. Just like geometry is an area and calculus is an area of mathematics. So when we think about the study of math, let's think about this. The study of mathematics is about numbers, quantity or values, shapes, and space. Now, how does that work? Why is that important? Because when we think about these things, number and value are two different things. If I were to write the number 3 down, you would see this squiggly line on the board, and you go, okay, I know that that's 3. Now, we as adults might understand that that actually represents 3 things. Then if I were to take out, say, 3 apples or 3 manipulative blocks, and I could say those are 3. So now I have a difference between a number and a quantity, or a number and a value. They work together, but they're individual things. And one of the things that's important for students to see is how they go together and why they work together. Now, when we talk about the things, the 3 things that we've created over here, they make up a shape. Sometimes that shape's a rectangle or a circle, or it could be a building, it could be any number of things. And within that shape, it takes up a space, and that space has length and width and height. And really, a study of mathematics is looking at the fact that everything that is around us, the chair you're sitting in, the computer you're looking at, the lights that are working, everything around you can only be created, used, or processed using mathematics. The precision needed in order to do the creation aspect of manufacturing requires very intricate and controlled mathematical understanding. Just like technology to create computer programs is required in order to do that. So the math is a huge part of our life, and it comes down to understanding these 4 things, but also their interrelationships, how they go together, because one by itself is not enough to actually understand and study mathematics. And then with that, we have what's called specialized notations. Specialized notations would be the addition sign, the minus sign, the equal sign, the multiplication symbols. And these symbols are very important for us to understand what operations we're going to do. And that's where we get into actually creating the equations and the algorithms that we're going to use, because that's talking about the process. Because mathematics itself is like a language. You ever thought about that? You know, we spend a lot of time focusing on reading, and we talk about how the English language or other languages that are spoken in the world, But really, math is a language unto itself. And it has things that are like subjects and things that are like verbs. And if you look at the syntax, you have to have a specific syntax in order to explain how the math works. And this becomes very important. I always like to tell teachers that are teaching both math and reading that they're bilingual. And they kind of laugh at that because they don't think that bilingual. You know, think if you're teaching English and Spanish or English and French or English and another foreign language, that you're bilingual. But if you're actually teaching mathematics, you're teaching a language unto itself, which is a real process for students to understand. So being able to understand why you're doing what you're doing with math is important. Now, when we talk about doing math, what does it mean to do math? Well, there are levels of arithmetic, and we're going to focus on arithmetic in this workshop here. So when we think about arithmetic, the first thing that we would want students to understand is how to count. And learning to count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and understanding that there are only 10 digits that represent our base 10 system called the decimal system. And that system can be explained with using place value, that every time we're working with math, everything changes on the nines. So if you were to count 1, 2, 3, 4, 5, 6, 7, 8, 9, when you go to 10, you're actually changing places. And just like you would for 99, 100, or 9,999, 10,000. So you have a way to actually explain how the decimal system works, being a base 10 system. So counting and place value are very important. Then the next level is addition and subtraction. Now in addition and subtraction, we start to understand how equations work. We start to understand the ability to compare things and combine things. Then we can move up to multiplication and division. And if you'll notice on the side of the screen, and for some reason that screen kind of got a little screwed up. The pieces are off just a little bit. Multiplication, division, and then exponents and roots being the level after multiplication. So in each one of these levels is a faster way to do what we've already done previously. Let me show you what that means. So when we look at counting and place value, counting from 1 to 9 and understanding those numerals, when we go to addition and subtraction, now we're doing fast counting because now we can do, I don't know why this slide did this, but it messed up on the transition here. But for addition and subtraction, it's now 3 plus 3 plus 3 equals 9. And we can still get to 9, but now we do it using whole numbers instead of using individual counting strategies. Then when we go to multiplication and division, now it's fast adding of the same number. So 3 times is equal to 9. And the next level after that being exponents and roots, now it's fast multiplication where we could say 3 squared is equal to 9. So every time we increase in our level of arithmetic, we're actually learning to do something faster that we already know how to do. And where it becomes confusing in math is when we throw in different words, our vocabulary changes. So when we think about doing math, the operations of arithmetic never change. So we add, subtract, multiply, and divide, and count. Those operations never change. We will always do that when we're doing mathematics. So the question is, what changes? So if we look at this here, I'm going to use a model here that's a 3 by 3 square. Now, I could teach to a student, I could teach them how to count 1, 2, 3, 4, 5, 6, 7, 8, 9 using a regular counting pattern. So I could teach this level of counting right there. Then I could teach them to see that they have a group of 3 and a group of 3 and a group of 3, teaching them how to do addition right there. Or I could teach them 3 times 3, in which I teach them this is 3 over this way and 3 up this way in doing multiplication. And then 3 squared being that this makes a square. Anytime you hear the word squared, that little the exponent there, the 2, means we've made a shape that's a square, and each side of the square is, again right here, this side and this side is a length of 3. So in each case, my model didn't change here. I could teach every level of arithmetic with this single model here in example to 9. But we need to know what does change. So what changes? Oops, let me erase my drawings here. So what changes? Well, what changes is the type of number we're working with. When we start out, we start with natural numbers, and then we move to whole numbers. And whole numbers includes 0. That's the only difference between natural and whole numbers. And getting students to understand how those whole numbers work and the values that they represent is a key piece of understanding the first levels of arithmetic, how we do addition, subtraction, multiplication, and division. And once we gain that understanding, we can move into integers and rational numbers. Integers being where we go less than 0, being -1, -2, -3, so positive and negative numbers, and then rational numbers where we're dealing with fractions and decimals and ratios. And that's where it becomes really powerful, is to see all the things that we've learned in the first steps of addition, subtraction, multiplication, division. We can now apply into some really fantastic things related to math. And of course, the algebra portion, if we think about having letters in our problems, and I know a lot of people kind of cringe at that, but having letters, all that's telling us is we don't know what it is. And so when we can start to express to students at a very young age that a letter simply means we don't know the value, then they start to look at things differently. So I love putting letters into problems very early. Kindergarten, first grade, it's not difficult to do, and the kids grab a hold of it fairly quickly. So when we're thinking about the math itself, we need to realize that everything that we're going to do, we're going to repeat. We're going to actually learn how to do it faster than what we did before. So that's why understanding those levels of arithmetic is so important. So why is math important? Now think about this. As a parent or an educator, have you ever had a student ask you, why do I have to learn math? I already covered this a little bit earlier, but this question is what what are all the things that you can think of that require math to create, understand, use, or produce? And if you just sit there and start thinking, you can create an endless list. But how often do we explain to students, to those that are trying to understand the math, how the math is applied into real life? How do we help them understand that the ability to even use a computer or sit in the chair that you're in, all of those things require mathematics in order to create and understand, use, or produce? And when we start to show the students how those things go together, this means being able to show them that the numbers and the values and the shapes and the space all require that understanding in order to put the pieces together. So if, let's say, I'm going to use something really simple. You're sitting in a chair right now. Well, the chair that you're sitting in, somebody may be on a couch or something, but if you're sitting on a chair, every piece of that chair had to be manufactured, had to be put together, had to be designed. And it could be something simple as a stool or something very complex, but every piece had to be designed, and those pieces had to be put together in a way that they fit properly and work together properly, which means someone had to take time to create drawings and use mathematical reasoning in order to assemble everything together. So math is incredibly important, and we need to help our students understand why that works. Now, the research that's been going on, there's been some incredible research recently. One was by Carnegie Mellon University and Dr. Robert Siegler, and he recently published a study with his team. And one of the things they found that was so critically important for students was that they had to have mastery of fractions and early division in order to do higher level math. And in looking at the study, this was a 20-year-long study. This wasn't something that was done over a 6-month period of time. They looked at students over their entire course of mathematical studies, so 20 years of time. And they said that there needed to be a focus on whole number division and fractions in order for students to be able to do that higher level understanding. The other thing that he found is that teachers lacked a firm understanding of the conceptual side of these concepts. And as we go through this today, hopefully I'm going to give you some things that you'll be able to see and explain a little bit of what I was never taught in school. I was never shown what I'm going to try to show you today through these slides. Normally I like to do everything live so I can actually do a little bit. I can do some things with the slides here, so hopefully it will convey correctly when we do this. But if we don't find a way to help not just our students but help our teachers be able to understand and instruct and deliver that instruction, that's going to be really difficult. And I know there's a lot of hullabaloo about the Common Core and different things out there. I've looked at the standards. The thing I will say about the math standards is it's two different standards. And because there's a math practice standard, which is the way the instruction needs to be shaped and delivered, and then there's the grade level standards, I think that becomes a really key feature in helping teachers understand how they need to deliver that. But unfortunately, how do we help our teachers be able to do that? And that's what part of my goal is to be able to help teachers understand how to deliver that instruction so that the students can understand the math differently than the way I was taught in school. Now, another group of research that came out was a practice guide from the Institute of Educational Sciences, which is the research branch for the Department of Education. The Woodworth Clearinghouse is the branch that actually publishes the practice guides. And in going through their recommendations, they found that intervention materials should include opportunities for students to work with visual representations of mathematical ideas, meaning students need to see the math in action. They need to see visual representations of why the math does what. If you just put numbers on a screen, if you just put, squiggly lines is what I like to call it, and the student doesn't understand the value or the shape or the space and the interrelationship between those things that go with it, then it's just a bunch of gobbledygook on the board. So when we use visual representations, we can explain things consistently and with reason as we progress through the levels of arithmetic, it brings understanding to students that really changes the way they look at math. And of course, that study also came out in the same thing and said that interventionists, meaning the teachers, need to be proficient in the use of those visual representations of those mathematical ideas. So in order to do that, we need to move and understand math in a different way than we have previously. And I think that's part of what's going on here in the United States is we're trying to move beyond teaching counting strategies. And for most families and teachers that I've talked to with students who have learning disabilities, I see they start out with that counting strategy, they learn how to count, but then they try to do addition, subtraction, multiplication, and division using counting strategies. They don't actually move into what are called whole number strategies in order for students to see how the math works in larger forms. So everything has to be counted out, and I believe that actually is detrimental to students' understanding of how the math goes together. Then we need to develop multi-sensory techniques for all the operations, meaning we need to be able to show how counting, addition, subtraction, multiplication, division, and exponents work in a multi-sensory way. It can't just be pencil and paper. We have to have manipulatives or visual representations that allow students to see the math and put their hands on it or use a mouse to actually control and manipulate the values, not just the numbers, but the values as physical form. And when they can do that, it starts to change the way they see the problems going together. One of the best examples I can give you for that is when my oldest son, who's now 25, but when he was 10 years old, we were buying a new house, and the real estate agent was showing us the house, and he had the MLS sheet. They still had MLS sheets back then. And he walked up to the agent, and he said, "Hey, I think this is going to be my room. Can you tell me how big it is?" And the agent looks on the MLS sheet, and he sees that it says it's 11 by 15. Now, my son Daniel goes, "Sweet, it's 165 square feet." Now, the agent immediately goes to the divine chalkboard in the sky and is trying to figure out whether 165 square feet is correct for 11 times 15. And finally, he looks at my son and he says, "Okay, how did you do that so fast?" And Daniel looks at him very matter-of-factly and goes, "Well, it's simple. It's 11 up, it's 15 over. That's 100 blocks, 6 10 bars, and a 5 bar." Now, that doesn't make any sense to you necessarily right now because it's hard for you to picture what he just did. But he looked at the problem as being an area problem and used the visual representation of that problem to solve the answer without going through the algorithm itself. He did it in a visual way with shapes rather than looking at numbers. And that created an understanding in him that pervaded all of his upper-level math instruction. he was able to put pieces together because he could see the math as values as well as numbers and the symbols. So it's very good to when they can do those pieces together. Now, engaging manipulators that demonstrate each step, and then, of course, developing that proficiency in the teacher, whether that teacher is a parent or an educator in a classroom or a tutor. We can have tutors and parents and teachers who are proficient, not just struggling, but actually understand it and can talk in a way that brings understanding. That's going to change the way math looks like in school. Okay, so let's talk about what this might look like. So think about place value. This is the first level of, in the first level of arithmetic, we're talking about counting. And of course, with counting, we would use unit counters like this. Now you'll notice here, this is what most of us were told this was the ones place. And I think ones is a way you can explain this place. But really, when we start to think about writing numbers, if I write the number 100, I'll try and do this with my mouse. Hopefully I can write in a way that makes sense, 135. So I write the number 135 here. Now if I were to ask you as a student, where do the ones live? Okay, well, it's kind of confusing because this is a number 1, isn't it? What we're really asking them is here. So one of the things that I like to do, and I believe is very good instruction, is to use precise identifiers. So you have a hundreds place and a tens place, and I like to call this the units place instead of the ones place, because ones can get confused with the value. So I'd rather be able to say that I have 1 as a value rather than 1 as a place. Now the other, so the values we have here, we have our 100, we have our 30, 3 tens, and 6 here in the units place. Now notice each place has a different color. So we have red for the hundreds, blue for the tens, and green for the units. This helps the students to clearly identify by color that there's different places that they're in. And this has been found to be helpful in, you'll see that in Montessori training, you'll see this in Cuisinart rods, you'll see this in all sorts of different manipulators out there, that color helps the students to identify values very quickly. So using those precise names helps to eliminate that confusion that the students can have. Now, then we need the students to understand that every number in here has its own place, and that value of that number can be represented physically by something that is scaled to size. So if you look at this unit cube right here, one of these unit cubes, if I have 10 of those, then it's going to make this length of 10. And if I have 10 of these 10 bars here, then it's going to make this shape of 100. So being able to have students understand and develop that number sense is another piece of the puzzle that's really critical for them to be able to understand how all of the mathematics goes together. Because this unit cube right here, this is really the building block of what we're going to do for mathematics. And if we can understand how that unit cube goes together and works in increasing size, it's really helpful. So look at this for just a second. I'm going to clear the screen up. I want to... all right, so if we look at this screen here, you'll see you have the little unit cube, which is a square. Then we have the 10 bar, which is a rectangle. And then we have the 100 block, which is another square. So there's a pattern that goes on here: square, rectangle, square. Now just think about this in your own. If I were to take the next guess, what shape should my 1,000 be using this pattern? So if I have square, rectangle, square, a lot of us would say it should be a cube because we were shown base 10 blocks that use a cube for the 1,000. And yes, 1,000 could be represented with a cube. However, it's really problematic for doing operations in base 10 because we want to be able to have students see that I put this slide up here. Here's my unit cube. Back to my pen here. Here's my little unit cube right here. Here's my 10 bar. Here's my 100 block. And then this is my 1,000. And notice that the pattern continues: square, rectangle. And if my unit cube is a 1/2 inch by 1/2 inch, this becomes a 1/2 inch by 5 inches. 5 inches by 5 inches. Now, 5 inches this way by 50 inches that way. Explains why you don't really see many 1,000 bars out there. They're a little big. Then when you go to 10,000, you have something that's 4 feet 2 inches or 50 inches by 50 inches squared. And in this case, the 100,000 right here, they wanted to make it up the playground like this, but they couldn't fit it on the playground, so they ran it down the sidewalk like this because it was so big. It was 500 inches long at 41 feet 8 inches. And the teacher who did this wrote me and said this was a 2-day exercise she did with her 5th grade students. And she said they gained so much number sense in just doing this exercise. It was actually painted on the playground. And then the principal of this school, who came to a separate training, when I explained doing this, he said, yeah, my teacher's the one that went out on the playground and did this. And I told her to go out and paint it, but I didn't realize how big it was. And that just tells us that when we think about numbers, we need to recognize how big those values get. Because we know that we look at our government officials and they talk about trillion. If we already know how big 100,000 is, we're not even in the millions yet. Think about a trillion. That's a lot of zeros behind a trillion. That's a really big shape. So we need to have our students understand that ability to have that number sense is a big part of their growing up. Now, addition strategies. One of the things about addition that's really cool is we're talking about combining values together. So combining things together, now you're going to see that I have color blocks that actually represent the whole value. So I have a 3 and a 4. So this pink area right here is a value of 3 that goes with the number. So the number and the value, number here and value here, go together. They represent the same thing, but they're in different forms. So then my 4 and my 4 bar right here go together. And then notice I've made 2 horizontal parallel lines right here. So this is a horizontal line, this is a horizontal line, which happens when I put my 3 and my 4 together, and then I can bring the 7 bar up underneath it, which is a different color, and now I focus on building this equal sign right here. So this equal sign is a huge part of everything we're going to do in math, because you're now going to put a tool in the student's hands that if they come to you and say, Miss Smith, is this answer right? Well, if they have the manipulatives, if they have the ability to draw this out, they can know themselves whether the answer is right because they have the ability to understand that equal sign means 2 horizontal parallel lines together. Are they the same length? So now we're able to overcome issues like subitizing. We're able to overcome issues like having students understand that the addition strategies go together and not using counting strategies, trying to use unit counters. We're actually using whole values to do this instruction. Now when we go to multiplication, the next level up, in multiplication we need to recognize that in multiplication we're always building rectangles and squares. So if we look at this specific slide here, we can see that I have the product or the area of 16. Now I can make that area of 16 by making a 4 over and a 4 up shape right here. Or I can make it as an 8 over and a 2 up shape here. Or as a 16 over and a 1 up shape, right like that. So I have the ability to make 3 different rectangles, and a square is just a special rectangle. It has equal sides. But I can make 3 different rectangles in showing how multiplication strategies work, because these are the factors of, I make my arrow there, these are the factors of 16. So 4 by 4, 8 by 2, and 16 by 1. And if you ever remember being in school trying to figure out what the difference was between a prime and a composite number, well, the simple way to look at this, if it's a composite number, I can build or I can compose multiple rectangles. So composite and compose go together as words to explain the difference between a composite number versus a prime number. And a prime number, one of the things here with a prime number is you can only make a line just like that. You really can't make anything other than a rectangle that looks like a line. It's still a rectangle, but looks like a line. So being able to show students how multiplication works from an area model or an array pattern is really powerful. And then getting students to be able to factor numbers. factoring is a very important skill, especially for going into algebra and higher levels. You need to be able to know how to basically decompose a number and break it down into facts itself. Now, when we do that, the next thing after multiplication is division. I love to ask this question because why we use this symbol for long division. We also use this symbol right here. And for those of you that don't know, the technical name for that symbol is called the obelus. And we use a slash mark like this. So I could put 16 and 4 right there, or I could put 16 and 4 right there. So these are symbols that were created in order for printers to put mathematics on a line so they could actually print mathematical problems for division on a line. Because fractions are division problems were actually set up like fractions, right, like this, which is why these numbers, these dots right here, actually are representations of those numbers in a line across like this. But the other symbol we use is this one right here. And why do we use this symbol for long division? Well, I've heard lots of different answers, but the one that I have found to be most effective is if I put a dotted line like this, and I put a dotted line like this, what shape did I just make? I just made my rectangle right here. And why is that important? Well, making my rectangle, I now link division back to multiplication. And we understand that in multiplication, we always have to build a rectangle or a square. When we move to division, what happens in division? Well, in division, we're actually given our rectangular square. We're given our total amount. We're given our dividend or the product in multiplication. And now, because we can actually see the fact that this creates our box right here, just like the 4 bars do, we can see that this is 4 up and how far over, and that's the division symbol that we had on the previous page. Let's see if I can go up here. So I'm going to draw my head. So if I go back up, it won't let me go up or down. All right, I'm locked on a page. Sorry. If we see this, that long division symbol is the same thing right here. So whenever you see this symbol, if you will just realize this is telling you how far up, and it's asking you how far over in the division problem. So you can put your number right in here, and this tells you how high. And if we use the previous 2 slides ago, if I change this to 2, let's say it's not 4, let's say it's 2, now you'd know that that would look like something like this. I know my drawing is just really bad trying to use a mouse to do this. But you can actually help the students to see how all of that goes together, to see that this would be a 2 up by 8 over rectangle. And then putting the pieces together, that in multiplication we would call this, we would call the numbers out here factors, but in division we call them divisor, dividend, and quotient. So understanding how these numbers actually work together is very, very important. So we need to deliver explicit instruction, and then by using that clear modeling with precise verbal and written expression, using a comprehensive manipulative that can cover all these things, we can develop that mastery in our students. Now, one more thing to go over here, let's talk about larger multiplication strategies, is for all of us, we were taught in school how to do double-digit multiplication, and then we went to double-digit long division, and those pieces didn't necessarily go together, and then when we got to algebra, it was like a whole new thing that didn't make any sense. Well, here we can see that the multiplication strategies, this is something that really helped me understand the way the math goes together. So traditionally, we were taught to do math, do double-digit multiplication right like this. And what we would say is we would say 3 times 2 is 6, and then 3 times 1 is 3, and then we put a 0 down here like this, and then we'd say 1 times 2 is 2, and 1 times 1 is 1, and then we'd add all that together to get 156 somehow. But if you guys just heard me say it out loud, if we actually added together what I said, 3 and 2 is 6, 3 and 1 is 3, 1 and 2 is 2, and 1 and 1, the answer would actually be 12. not 156, because we eliminated the place value from the words that we said. So by using the expanded form here, by using this and putting the values into an expanded form or place value notation, and now doing the multiplication, it changes the way we see the problem. So now I can multiply 3 times 2 and get 6. I can multiply 3 times 10 and understand that I'm multiplying 3 tens to get 30. Then I can multiply 10 times 2 and understand I'm getting 2 tens to get 20, and then 10 times 10 to get 100. And this explains the process in a much clearer fashion for students than keeping it in the condensed form. The other thing it explains is this 0 that we were taught to write in here, if you actually do 10 times 2 right here, what number do you write? 20. Well, 20, isn't that 20 right there? That's the 20 we're talking about. Now, over here in the modeling, and I would typically model this first. It's hard for me to talk about modeling it when I can't show you physically building it. But here we have a rectangle that we've built. Remember we said in multiplication, you always have to build a rectangle or a square. And in this case, my over dimension here is 12, and my up dimension here is 13. And I can show that it's a length of 10 plus 2, and it's a length of 10 plus 3. And in doing that, you can see each piece of this right here, each piece of this is laid out here. So my 6 is right here. Here's my 6. And then my 30 is right here. 30. And then my 20 is right here. And my 100. So I'm able to build and construct and model what's happening in the multiplication problem, and then each step of the multiplication, and then down here in the addition part of this problem to show the total of 100, 5 tens, and 6 units for 156. Now keep in mind, I'm going to clear this off for a second. Keep in mind of this shape right here, this shape right here. Now watch this. When we go to the next slide, is this the same shape? This right here is the same shape as what we just did on the previous slide. It didn't change. And so, again, now looking at this, now I have 10 plus 3 up and 10 plus 2 over. So what changed? My model didn't change. What changed is the question I'm now asking regarding this quantity. Because in multiplication, I have to find out my product or my total. In division, I'm actually given how much do I start with. I firmly believe that with manipulatives, teaching division is easier than teaching multiplication. So now the question is, how many 13s can I count out of 156? Well, if we look at this, we can tell. So if I have 13 up and I'm looking at this over, how many 13s can I get? Well, here's 10 and 2. So if I multiply 10 times 13, I come up with 130. Which then I can subtract 130 from 156. I don't have to worry about bringing the 6 down because I'm actually doing the multiplication correctly. I'm using clear language and I'm explaining using the whole numbers. Then I can multiply the 2 times the 13 to get 26. Because 156 minus 30 is 26. 2 times 13 is 26, leaving me 0. Now, if this had been 158, and let's say I had 2 little unit cubes sitting out here because I couldn't fit them in here, that would be my remainder. So I have a leftover down here of 2 instead of 0. I would have a remainder of 2. And why is it called a remainder? Well, it's called a remainder because it doesn't fit inside the rectangle. It remains outside. But this is really a remainder of 2/13. And if I was actually able to divide up my 2 little unit cubes here by 13, which is what the division problem is, 2 divided by 13, then I could actually fit them along this edge of the rectangle because they would fit. Now, so you've seen multiplication and division, but now let's do one more thing and look at this slide and watch the model. Is this model the same model that we have seen in the last 2 slides? It is. But what are we doing now? We're doing multiplication of binomials. in which we had to use what we were taught in school typically was called the FOIL method. And in using the FOIL method, it was x times x, and then x times 3, and then 2 times x, and 2 times 3 to get x squared plus 5x plus 6. And I believe that the FOIL method can be confusing for students. I like to take these binomials and put them together like this. So if I have it set up like this, I can then do my multiplication just like I did in my 10 times 12 and my 10 times 13. And again, I'm able to come up with x squared plus 5x plus 6, but I can see this is x plus 2 over and x plus 3 up. Because if we're able to help our students see early on the patterns that occur in math, the repeated pattern, when they go to higher level math, they're going to see those same patterns over and over and over again. So, in conclusion, we need to move beyond those counting strategies. We need to use concrete visual representations. We need to engage color to distinguish and identify and demonstrate each step. And then provide teachers with the tools to develop that proficiency in themselves and in their students. All right, Jennifer, we're up for questions.
Perfect. Norma's got quite a few in here. So Norma, I'm going to go ahead and have you just start fielding them out, and we'll see how many we can get through. Norma? I might have muted her by accident. Let me check. And, you know, Dan, I messed up your slide, that one that you were saying. I don't know what happened to this. I saw that I messed it up, and then I tried to fix it, and I think I didn't save it after I fixed it.
I should have just run through them. It's all right.
Well, yeah, that's definitely my bad. Okay, Norma, are you there?
Hi, Jen.
Hello, Norma.
Hi. Sorry about that little delay there.
That's
I
right.
was trying to open a window, and then it blanked me. It got me out. Anyway, so we have a number of questions and a number of comments. So I didn't want to leave out the comments because they weren't phrased, put into a question. But okay, so here we go. First question is from Heather. Is Lindemood Bell tutoring effective to help with dyslexia and math problems?
I really can't speak to the specifics of Lindemood Bell.
Okay.
I've heard people have success with it, so I think that's something that you'd have to check out yourself and get referrals and talk to other people that have used that system.
Okay.
Unfortunately, I can't answer specifics to that program.
Okay. Next question is from Robin. Are educational therapists familiar with your approach, Dan? Can we find one in our area?
I have been to the Association of Educational Therapists National Conference several times. To say that educational therapists as a whole are familiar with the approach, I don't know that I could say specifically. There are certainly educational therapists that are using this approach or approaches very similar to this, and understand the value that comes with it. As far as where you're at, Robin, I wouldn't know whether I could find someone there for you or not. The cool part is, if you're a therapist or a teacher, there are ways to learn and understand this that are relatively easy and not that expensive. So it's really more of an investment of time and understanding in order to do that. So if that's something you're interested in, I'd be glad to talk to you about.
And the same question from Robin is Tomatis and listening program helpful for anyone out there? They say they are helpful in Dyscalculia. I'm
not familiar with either one of those programs.
Yeah, I don't know if it was misspelled incorrectly when she typed it in, but it's TOMATIS, listening program.
Yeah, I'm not familiar with either of those. Nope.
All right.
Sorry.
That's all right. So Connie, this is not a question, it's a comment. She goes, my son is 17 and has been diagnosed with dyslexia by a neuropsychologist. He has a high IQ, very high math ability in early years. He still has difficulty with basic math facts, algebra, trig, and calc. We have difficulty with math teachers understanding how his difficulty relates to math. So
I can understand that. My middle son, as I said, he had dyslexia, but he also had central auditory processing disorder. So having people understand how difficult it was for him to do math when he did other things really well. And to give you the comparison, he, at 17 years old, he won the national championship for BMX men at the national level. this huge, physically he's a very gifted individual, but when it came to mathematics or reading, it just was another whole ballgame. So being able to express those things is oftentimes difficult for students that have sometimes very high IQs or have learning disabilities that prevent that.
Okay. Rebecca, let's see. Oh, she was, this is a very, I'm going in the order that the questions came in, and it was when you were talking about a study early on the, I guess, the Clearinghouse. What are, because are they still working on that study, developing a tutoring program? My dyslexic son participated in a study at his school recently, testing a teaching program developed by Carnegie Mellon. We're in South Hills of Pittsburgh.
You know, again, unfortunately, I can't answer for Carnegie Mellon what Carnegie Mellon is doing, but I know the research that they did was quite extensive, and they had a lot of great information in that study to talk about what was needed in order for students to be able to do higher level functioning.
Okay. Let's see, Catherine, are there any multi-sensory methods for calculations past the level of exponents, such as functions and trigonometry?
When you come to, when you get up past Algebra 1, math becomes much more abstract, and it's harder to do something in a physical representation. You can do things on a computer that will represent what's happening, like with a parabola or different kinds of things in trigonometric functions, but to say there's a manipulative out there, it's a little trickier to do that where it's a multi-sensory thing as a physical thing. On the computer, there are certain things that you can do in order to show some of those, what those functions are doing or why they apply in that direction. But you can also do three-dimensional things on the computer that you can't necessarily do in real life with physical things.
Carrie's question is there a better color version of the tiles to this compared to Math-UC? That's when you were doing the 3 plus 4 plus 7 and the color. I think that's what she's talking about.
Is there a better color version of
the tiles
compared to Math-UC? I'm not sure I understand the question.
Okay.
Math-UC has Math-UC. I have carried Math-UC for many years. My role with Math-UC is I actually sell to schools. I don't sell to individuals Math-UC. And I think Math-UC is a great program for direct, intensive, individualized learning. It's a complete program, and I think it does a lot of great things for students. So I'm not sure I understand the better color version of the tiles.
I think she's just looking for. I think she's just looking for alternative color scheme rather than the colors that are used in the Math-UC program. So I think she was just looking for the same type of product.
The Teach for Mastery, the company that I have, we created our own manipulatives because we came out with a different product. It's a different product for Math-UC. It's designed for a different way of doing things. Not necessarily different. How to say? They're similar, but they're different. The products are different. Math-UC is a complete curriculum where the perception series is more like targeted instruction. It's an intensive intervention. So, so if I don't know if that answers your question, Carrie, but I'd be glad to chat with you about that and see if there's something to help you with that.
The next three questions are kind of high school level. Paula actually this is an excellent question. She goes, my daughter is dyslexic and has dyscalculia. I am Orton Gilliam trained and taught her how to read. She's in 7th grade, reading at the 8th grade level. Her math level is at 4th and 5th grade. Her main struggle is with her short-term memory. Is there any materials to help her with building her short-term memory and to help her with sequencing needed for math?
Oh, that's a great question.
It's a really great question.
One of the things that I have learned, and the thing that I've seen happen in classroom settings, is there seems to be this rush to get rid of the manipulatives, to stop using the manipulatives. And one of the things that I found, and my wife and I found in teaching our son, was to let him use the manipulatives for as long as he needed them. And what we found is he eventually weaned himself off of using the manipulatives, and then he had his own confidence. But so often I see where we're trying to get students to see the manipulatives and then put them away because they're slow. Well, if the student needs that visual representation in order to put the pieces together, I see absolutely no reason why the student shouldn't be able to use them. We let students use calculators all the time. What's the difference? And so I think it's a huge difference between a calculator and a manipulator, truthfully, but we need students to understand how to do that. So if your daughter is struggling with that short-term memory, that's what my son struggled with, is being able to have those pieces available to them to be able to do the math physically, so he knew he had the right answer. And yes, it will be slower than just doing the pencil and paper that you and I might know, but it gives them the confidence and the understanding in that repetitive motion, and builds kind of that muscle memory and memory in the brain of how those pieces go together. The other thing that I would suggest is try and change the position that she's doing the math in. Sometimes we don't realize that when we're doing math looking down at a table and sitting, that we're changing the way we process information. And sometimes if you get the student to lift their head up, so if you had her doing the math on like a whiteboard, standing up and writing the problems using a little more of a gross motor skill than a fine motor skill with a pencil, you may find that she actually grasps things a little bit differently or faster. I can't guarantee that, but that's one of the things we learned with Chad, was getting him to stand up and do the math on a board rather than sitting down, looking down, created a big change in his ability.
Interesting. High school student with dyslexia in an Algebra 2 Trig accelerated program does well on quizzes and average on tests, but will fail a quarterly exam. Teacher states he has the ability to succeed, but his struggles are not conceptual errors, but rather computating errors. Any suggestions? When kids are doing well on quizzes, but then at a quarterly, they fail. Not sure.
Really hard. It's, again, you run into different things with different students. Some students just don't test well. I've run into that where I can sit down with them and they can go back and forth with me, and the minute you put the test or there's that pressure of the test on them, they freeze up and they kind of don't want to, or aren't able to articulate what they know. And for me personally, this is where I believe teachers and parents are so incredibly important and powerful in the process, and where technology is never going to be able to take this next step, is I as a teacher can understand what my student knows better than any test could actually measure. Because a test is only going to be able to deliver a specific strategy or a specific way of looking at doing a problem, where I as the teacher or the evaluator, the assessor of that student, can see all the different ways that they can do that problem. And sometimes the test is just a way that they may or may not have seen before. That I've seen test questions that confuse me, and I'm like, this doesn't make any sense to me the way this question is even worded. And with just a little bit of change, the question makes a lot more sense. So when students struggle with quizzes, I often wonder whether it's more test anxiety than it is actually understanding what's going on with the math itself.
Mm-hmm. I think sometimes I have found, just with the parents that we speak to, we've always suggested, you have the written component of the test. Obviously, you're answering the questions in class, but in your extended time, to go to the teacher, and as the teacher looks through your test to see where you have errors or you've gotten the problem wrong. Now it's the oral component of the test where they get to talk out or speak about how they thought through the process and through the test. And that has helped in getting partial credit and realizing, well, they didn't understand this word or language, they missed, so yeah. It gives the teacher a little bit more insight as to
absolutely, absolutely. I'm a firm believer in when a student on any test, if they get a problem wrong, I'm a firm believer in going back to that student and having them explain to me what they did.
Yeah. So
many times it's a language issue, or it's a way they interpreted what was going on rather than actually misunderstanding.
Correct. One more question. I know we're running out of time. How do you encourage a high school student who scores who's a very visual spatial, that's what their strength is, and wants to study architecture, engineering, urban planning, but is fearful of the math in college because of, vocabulary, language, short-term memory, and sequencing. How do you keep that? How do you encourage that student to take that challenge on?
I would encourage that student, you want to become an architect, go for it. Do everything that you can, and yeah, the math is going to be, a part of that. The colleges today have a lot of ways to help students who struggle in those areas. I can't remember the name of what there's a resource center at the colleges that actually is designed to help students who have difficulties to get accommodations in those classes and to be able to work through those things. So I would definitely recommend that if the student's now looking at colleges, that they actually query the colleges about what does that mean, what kind of help is available in order to do that, and hopefully that will be advantageous. But if that student has struggled with math all their life, let them, going back through and understanding the basics and understanding the pieces that go together is really important.
Okay. Do we still have time, or are we out of time?
I think we're past our time, actually.
Okay.
Yeah, we're past the time, but what we can do is there are several questions in the chat box that have been coming in, and Angie and Dan have agreed to go ahead and field out these questions, and we'll we'll get all the answers out for them because there's just so many of them.
Okay.
And we'll
Which is
get them
great.
out
I
to
appreciate
everybody.
that.
Yeah. Well, we answered 11 questions, so
that's really good.
Yeah.
That's good. And I think just to point out what you were saying on that last one, Dan, is a lot of times these kids get all the way up to college and we just don't realize the holes they have in the very, very basics of math, and they have to fill those holes first. They just are not going to be able to, move on to the higher level math if they have the inability to understand it at the, earliest point.
Right. Right.
So. Okay, well, you know what? This has been a wonderful session. We plan on doing more with Dan because this is just the beginning of, the amount. There's just so much to gather. So, Dan, we want to thank you for joining us today, and I will meet with you to get to the rest of these questions.
You bet. Sounds good.
All right. Have a great day,
Thank
everybody.
you.
Bye-bye.
Thank you, everybody. Appreciate you coming.
Bye-bye.